Welcome to Hartman Math. Before we get to our lesson on nonlinear inequalities, let's go ahead and work through this warm-up on graphing rational functions. Go ahead and pause here, work through it until you got it. Let's start by factoring both numerator and denominator. And we do notice that we have a common factor in the numerator and denominator, and we know that's going to create a whole. And if we were to cancel those out, here's what we have left. So we're going to get our y-intercept from here. As it does not have one, as we tried to substitute in 0, we get 0 divided by 0, which is undefined. X-intercepts come from the numerator. Horizontal asymptote, it does have one. Degree 1, so it's leading coefficient divided by leading coefficient, y equals 1. Vertical asymptote from the denominator at x equals 0. And we've got a whole at 2 comma something, so let's substitute in a 2 and figure out what that is. 2 comma 2.5. I think we've got enough information with what we've got here. We're going to go here, and then we're going to go here. This is lesson 2.7, Nonlinear Inequalities. Essentially, we're talking about polynomial inequalities, and then later we're going to look at rational inequalities. All the things that we've been studying in this unit, just applied to inequalities. So we can do things like factor, but unlike equations, were we to factor this, we would not say factor is less than 0, factor is less than 0. So it's just not that simple. So one technique is to, once we find the critical numbers by factoring, -1 and 3, is to test the intervals. Pick a number over in this region here, test it in the original inequality. Is it true or false? Same thing here, and test all the intervals. Essentially, here's a summary. If you want to pause it here and take a look, but here's a summary of how we test the intervals in a polynomial inequality. All right, example number 1. Solve, graph the solution set. So we're going to factor first. We would get critical numbers at -1 and +6. And then we're going to test the interval. We would try something like -4. And we could do it here or here. Might be easier in the factor form. If we substitute in -4, we would be talking about -3 times -10 is +30. Is that less than 0? It is not. And then we could try something in here. I always kind of like 0. 1 times -6 is -6. Is that less than 0? Yes, it is. And then over here, 7. 8 times 1, is that less than 0? It is not. So we test all the intervals. And since it's true here, as far as our graph goes, that's where we're going to essentially shade. And it is less than, strictly less than, no, or equal to. So we could either use open points or similar to interval notation, and the one the book likes to use here is parentheses here. If it had said or equal to, we could show it with a bracket. And now if we're trying to solve, we basically want to mimic the same thing from -1 to 6. And there's our algebraic solution in interval notation. All right, checkpoint. Go ahead and do the same thing with this polynomial inequality. Graph the solution set. Solve it, pause here, work through till you're ready. All right, the key here is we definitely do want to have one side be 0, because that's how we're going to compare and get either positives or negatives, and that's how we're going to get the critical numbers as well. So we're going to subtract the 7x squared. Let's make sure we put this in the correct order. And then it's factors. We can factor out the common factor and then factor out the trinomial. And so we're going to get critical numbers at 0, 2, and 5. So that's where we've got our marks there, 0, 2, and 5. And then if we test the intervals, false here, true here, false here, true here. You might notice kind of the alternating pattern. That doesn't always happen, so don't assume that it will. And this one does have the or equal to, so we're using brackets or close points in our graph. And then same thing in our algebraic solution, true here and true here, so from 0 to 2 and 5 on to infinity. So we can also solve the polynomial inequality by graphing. So we're going to solve this by graphing. We're going to factor to look for the x-intercepts. So we've got x-intercept at 0, x-intercept at -2. It's third degree with the positive leading coefficient, so we know that it's going to start low and end high. And at -2, since it's first degree, it's going to go through it. And then at 0, since it's to the second power there, it's even, so we're going to bounce right there, and again to finish high. Now what we're looking for is regions where we are below or on the x-axis. That's how we're interpreting this. Where are we below or on the x-axis? So that would be here, and that would be at this one point. So the way that we list that one single point algebraically is we use set notation and just list that one point. So we got our interval here from -infinity to -2 bracket because it's on the x-axis at that point. And then just over here with the one point, it's the braces. If we did not have the or equal to, this would just be parentheses and we wouldn't need this one at all because it would have to be strictly below. And that would be the only region that it's below. All right, example number 4, unusual solution set solve. We got part A. I don't think that one factors. And in fact, if we were to kind of go through quadratic formula on that, or completing the square to look for critical numbers, I think they would only be imaginary. So that means that on the real number line, there are no critical numbers. And so when we just pick a number to test, we're testing the entire number line, the entire interval. And if we were to test 0, we plug in 0, is 12 greater than 0? Yeah, that's always true. So if we were to kind of look at this in terms of a graph, we're saying where is our graph above 0? Always. So our interval is from -infinity to +infinity, all real numbers. As opposed to this one for part B, same thing, doesn't factor. We could attempt a graph, we could do the quadratic formula and come up with the same issue. And then we would be looking at where is the graph below or on the x-axis. Or if we tested an interval plugged in 0, 7 is less than or equal to 0, that's not true. So where is our graph on or below the x-axis? It isn't at all. So in set notation, that's like a 0 with a slash through it. Careful that that's not how you write your zeros. This means the empty set. Essentially meaning no solution, but in set notation, this is what we use. It's the empty set. There's nothing in the set. There are no x values that make this true. So those are some of our unusual solution sets. All right, so now we get to rational inequalities. Start by doing this algebraically. So again, we want to be able to compare to 0. So the first step would be to subtract 1 from both sides. And then the second step is to write it all as one fraction. So we're going to need to have a common denominator of x minus 3. So take our -1, multiply top and bottom by the x minus 3. that puts it together as one fraction. And then we could probably combine like terms here and simplify this. 2x minus 2. And then now we're looking for critical numbers. Critical numbers in this case would come from numerator and denominator. So numerator, if we set it equals 0 and solve or factor it out, we're going to get positive 1 and positive 3 from the denominator. And then if we test regions, we can go all the way back here. So if we did 0, we would get negative 5 divided by negative 3, so 5/3. Is that less than or equal to 1? It is not, so false. How about trying 2? So we get 6 minus 5 is 1. Negative 1 in the denominator, so 1 divided by negative 1 is negative 1. Is that less than or equal to 1? It is, so we're true there. If we try something like 4, we would get 7 divided by 1 is 7. Is that less than or equal to 1? It is not. False. And so here we are. And now we got to be a little bit more careful here. It does say or equal to, which is going to imply brackets, but we also have division in this problem. We're not allowed to divide by 0. So any critical number that came from the denominator, that would be negative 3, cannot have a bracket. It cannot be 3. That would cause us to divide by 0. So that's going to have to be a parenthesis there. So there's our graph. And then the solve part that goes with that mimics the same thing. Bracket 1, comma 3, parenthesis. Remembering that you can't divide by 0, so 3 is not allowed to be part of the solution, and that's why we have the parentheses. They say very close to 3, up to 3, but not 3. All right, so checkpoint, go ahead and do this the same way. Pause the video here as you work through. Once again, we're going to want to get one side to be 0. We'll start by adding 3 to both sides. Need a common denominator, so multiply top and bottom by x minus 3. Again, we get 4x minus 11 over x minus 3, greater than or equal to 0. So we've got critical points at what, about 2.75, 11 over 4, and 3. And then if we test them, true there. That slim range in the middle, false there, true here. So all these are true up to 11 over 4, which came from the numerator, so we can have a bracket there. But the other part on the 3, again, can't be 3, came from the denominator, so parenthesis at the 3 on to infinity. So the last thing we're going to look at is to be able to apply this idea of nonlinear inequalities to situations where we might need it. For example, what is the domain of this function? Well, in terms of the domain of f of x, the parent function, f of x equals the square root of x, what was inside the x had to be greater than or equal to 0. So we would say 100 minus 4x squared has to be greater than or equal to 0. And now we're looking at a polynomial inequality. So we could factor that out. We get the critical numbers at negative 5 and positive 5. We can test the intervals. So like negative 6, we do it here. So it will be 36 times negative 4. Add the 100. Is that greater than or equal to 0? No, it's not. If we try 0, we get 100 greater than or equal to 0. True in the middle. We're going to be true out there. So it would be false out on the outside as well. So false, true, false. It does have the or equal to, so we're going to go with brackets. And I just said find the domain. We didn't totally need the graph. We did use the graph as our testing our intervals to come up with bracket negative 5, comma 5. Bracket would be our domain. That's it for today. I'll see you next time.